Hey everybody, welcome back to the Pomerium live stream. Today I'm hanging out again with a couple of my coworkers, Bobby DeSimone, who's the CEO over at Pomerium, and my buddy Caleb, who's over on engineering. Today we're going to be, before we get into it, let's kind of dig into what Pomerium is for folks that might not be aware of it. So it's a open core identity aware proxy, and this gets set up, you self-host it on your network's edge, and that's kind of where we live typically. There's a few pieces in there. One of them that we're going to touch on today is the databroker. And but before we get into that, Bobby, I don't know if you want to maybe kind of give a bit of historic about Pomerium and maybe even just a little deeper what it is.
Yeah. So as you said, it's an identity aware access proxy. It was very much modeled after some of the core ideas coming out of Beyond Core and Uber proxy coming out of Google, which was the idea of, hey, we need a better way to access internal resources without depending so much on perimeter-based security or what you're able to touch on the network, right? This idea that just because you can reach it, you should be able to access it was really falling apart. And so Google came up with this idea, which is what if we use identity and your context as the means to whether or not you should have access to something instead of just whether or not you can touch it on the network. And so Pomerium, very much an implementation of that. Architecturally, it is a reverse proxy under the hood, or like a load balancer, ingress, egress. And so I think thinking about and kind of framing this conversation I'm excited to have around the lines of the unique challenges of where we happen to sit in infrastructure is a good way of priming it up, I hope.
Cool. Awesome. And so Caleb, I was mentioning the data broker. So why don't we kind of dig into that a bit, before we talk about some improvements we've been working on? What is the role of the data broker in an identity aware proxy?
Well, do you think it'd be good to talk about why, historically, why the data broker?
Oh yeah. Sorry, that's good call. So why does it exist?
Sure. So Pomerium's sort of broken up into logical components. The first stage is authentication. That is, a user has to log in. That's done through an identity provider like Google or somebody like that. And we get back a session. And that all of our identity providers pretty much are very similar. They either are very similar or are OIDC. And so they have these tokens that represent their session. And then we do have, that's the first component, is this authenticate. And then there is the proxy itself, which is receiving the requests and forwarding them upstream. And then we have this authorized service, which for every request, we make sure that the user who's initiating that request has access to the route they're trying to get to. Mm-hmm. And that involves looking at this session and seeing what their user ID is, what kind of groups they're part of, all that kind of stuff. Early versions of Pomerium, we stored all the session state in a cookie. And so that would be sent to this authorized service, and it could read the cookie and make its decisions based on that. Sort of the first challenge you're going to run into doing that is that cookies are very limited in what they can store. Now, you can certainly encrypt them so they can be secure, but since they have a limited size, and what is that limit is not even a very easy thing to define, because it really depends on browsers and things like that. And it is very easy to blow out that cookie, actually, because often it's the case that with identity, you can be a member of a lot of groups. You can have very large claims. Like one of these identity providers actually stuffs your entire profile picture in as a claim.
Oh,
so,
wow.
there's like a meg claim just sitting in there. Yeah, and that's not going to fit in a cookie. So so that sort of brings you down the path. Okay, we got to store state somewhere. We can't store it in the browser anymore. And that's kind of where this data broker comes from. And the next stage of that was sort of a group cache approach, or think of it like memcache, where you have a cache of data that all the server instances can share and have access to. But it's not necessarily, it's not like a database, it's not reliable, but it's there as an easy way to access data. As time went on, more features were added to Pomerium, which sort of changed the way we thought about the data broker, and made it so that we sort of switched models along the way. So we implemented directory sync, and so rather than simply getting user identity information from claims in a token, we could now get them through actual calls to like the Google Groups API or the Microsoft Azure Active Directory API or these kinds of things, and then sort of merge those two data sets together. Well, that's an offline process, that doesn't happen. It's not initiated by the user. It's a background thing. Okay. And then there's also this, we want to refresh tokens. A user logs in, their token's good, let's say for an hour. Well, we don't want to have to log in every hour, so we refresh it in the background. And both of these things sort of require something more persistent, not user initiated. And that pushed us in more of a direction. We started with Redis and eventually went to Postgres for storing this kind of data.
Okay. Yeah, it's kind of funny because when I use ChatGPT sometimes or a model, it likes to recommend Redis, and I know it's not Redis.
Yeah, in some ways Redis worked well because our requirements for the data broker, we don't need like a full-fledged relational data model that you get from a database. Okay. We're mostly just storing keys and values. And so Redis lended itself well to that. One of the requirements that we eventually added was, in addition to sort of this directory sync, we added external data sources. For example, geo IP data, like to know what region an IP address belongs to. So like, say you could create a policy that said, I don't want users from Russia to access my website. If you wanted to do something like that, there are geo IP databases available, and we can load them as an external data source into Pomerium. But that data is represented as IP CIDR blocks, like ranges, this IP to that IP. That is more complicated than just a key value lookup. And Postgres has indexing to do that built in, just ready to go. So that's kind of what pushed us in the direction of, we're just going to only do Postgres because it has all the features we need for all of the sophisticated indexing. So that's kind of why we went that direction. The other reason I think is that, if we were building a SaaS product, we might use services that a cloud hosting provider has available, like DynamoDB or something like that. We might build a more complex model of services. Like instead of having just the data broker, we might have several systems that do different things. Maybe there's the geo IP service that goes and does a lookup. But Pomerium's a product that users install in their environment. And having a very complex system with lots of services is really hard to install and manage. And so that's not really the direction we want to go. And then to require DynamoDB means like, okay, it only works in AWS. And what if you're not in AWS? And even though most of our customers are on Kubernetes and in cloud environments, there are some that are basically on bare metal or even air-gapped. And in a situation like that, you really are very limited in the kinds of services you can depend on. And the nice thing about Postgres is it's available everywhere. You can run it in the cloud, or you can run it locally or in a Docker image or whatever. So it was a good system that checked all the boxes and was easy in that sense to deploy. However, the challenge with Postgres, as we have discovered, is that, whereas maybe 10, 20 years ago, every company had a DBA, somebody who was an expert on a database, and they knew what kind of hardware it should run and how to index things and all the rest of it. That job seems to be gone. Nobody seems to do that anymore. And so the sort of knowledge about how to run a database is lacking, which makes that decision to use Postgres a little bit like, well, yeah, it's easy, but it's not easy to manage because nobody knows how to do that anymore. And so we've sort of run into that from customers, and they come to us with like, well, how many CPUs do we need? And it's like, I don't know. I'm not a DBA either, so it's that's hard to be fair, you only run into that at scale, right? Like a single Postgres server that's really simple could handle quite a bit of load, but at scale is when you start to have to worry about that. And so that's kind of the deficiency of the Postgres approach, if that makes sense.
Yeah, and I mean, we do have some customers that have very large scale. So I guess that kind of brings me to my next question, or good segue is like, so you've been doing a lot of work on the data broker recently. I don't know if you want to just maybe kind of talk about some of the improvements or changes you've been making.
Sure. So we currently support two storage backends. There is a Postgres backend, and then there's an in-memory backend. But in reality, the in-memory backend is really just local for development purposes. It's not intended to be run in production. So it has some deficiencies. I mean, one is if you restart it, it's going to lose all of its state. The practical consequence of that is that all your directory information is gone, has to be refilled. All your users are logged out. So that's kind of not great. And then it only works for a single instance of Pomerium. So if you have two data brokers, how can they talk to a single in-memory database? They can't. So that doesn't really work. Whereas the Postgres version, you can have multiple instances of the data broker all talking to the same Postgres database. So so that's why the Postgres is really the only supported production one. And we had this question of like, well, the Postgres has turned out to be a requirement, that a dependency that is difficult for some customers. Are there changes we could make to not require Postgres anymore, but still have some of the benefits that we are getting from Postgres? And that's sort of the direction the last few months we've been looking at things we might be able to do to improve it. So the first one was we are adding a file-based storage backend. So it's rather than just the in-memory, you can also use a local file. The benefit of that is if you restart Pomerium, it can resume where it left off. So we're not losing all the state anymore, which is a pretty big win. And the truth is there are plenty of key value on disk stores which provide very good performance and have all of the features necessary to do what the in-memory version is doing. So pretty much that's all to benefit. There's nothing really lost in terms of I mean, performance is very similar and all that sort of thing. So we're adding this file-based version in order to have another backend that you could use, and maybe it would be the only backend that instead of the in-memory, we would just use this instead.
Okay.
But that's one improvement we're making. Okay.
Yeah, and so like I guess you said it's a KV, so like pretty much everything that we store really is key value. It's not like super complex relationships and stuff like you'd have in like a relational database.
Yeah, that's right. So it's a little more. We have basic get and set and delete operations. We have a listing capability. In addition to that, we have sort of a watch mechanism, a synchronization mechanism, where I can be, rather than having to poll for changes, I can say, hey, I'm going to listen for changes. You tell me whenever a change is made, and it pushes it. And so we have that mechanism, which can be pretty tricky to implement with something like Redis. Now Redis does have some primitives to do that, but that's when you start to be like, oh, a basic key value store is not sufficient. And then, like I said, we also index some types of data in ways that can be a little tricky. So that's another part that can get a little complicated.
Okay.
Yeah, I think like I think maybe what might be interesting to folks, or would certainly be interesting to me, is like there's kind of like a meme, and for good reason, which is like if you're thinking about data storage, like I think of that normal distribution curve, that it's like Postgres, and then like the midwit is like all these fancy NoSQL or on device or at edge storage mechanisms, and then like the Jedi Master back at like super smart is Postgres again. And like I think that's generally true, and like Postgres is still going to be supported in Pomerium. I think it's like, especially if you're running like a SaaS or cloud app where you can hire your own DBA to manage the performance tuning of your storage backend. It still is a really sane default choice, as is like SQLite, for example, for like, and we can talk about this in a second, for single replica or like, situations. But Pomerium and maybe others too is in a unique situation of like where we happen to sit architecturally at edge, a lot of the constraints that Caleb was talking about. And I think it might be useful to even talk about, like, this has been, multi-year of, we've considered many different types of storage backends, from, most simply, which we still have, which is in memory, to like group cache, which is kind of like an expansion of that. I've been personally sort of obsessed with some version of group cache, as, because it has a lot of these, from an operator point of view. And that's like something we have to think about a lot at Pomerium, is like, because we are self-hosted in most configurations, we have to think a lot about the operator experience. And so a lot of our design decisions come around making Pomerium as easy to operate as possible, because like it or not, it's not just managing Pomerium, it's going to be Pomerium and whatever data backend our customers and open source users deploy as well. And so it's a non-trivial lift to say, hey, here's Pomerium, which has its own operator configuration surface area. And also, you kind of have to be an expert in Postgres. And so we've been trying to tune for that operator experience, the performance we see. And it's like, it's a really challenging set of trade-offs, as well as being, where we are at edge and some of the scale patterns we see. I don't know, maybe I'd open this up to like Caleb too, which is like, we've looked at like a lot of different storage backends. I touched on just a few of them. I'd be curious, like, what interesting things you found in exploring. You eventually settled on Pebble, and you talked about some of the benefits, being relatively simple, high performance, kind of a drop-in replacement for in-memory. What are some other surprising things you found when looking at kind of the short list of, storage backends you investigated?
Yeah. So, well, first, for the file-based approach, there's actually a lot of key value stores available in Go that we could have used. Went with Pebble because it's the storage engine used by CockroachDB, so has a lot of testing. It's sorted, which we do need sorting, and so that's good too. And it's good performance. It works well, and so it's sort of, that was a conservative choice. There's certainly others. There's different, like Bbolt and other things like that, but it just seemed like Pebble was a nice way to go. The downside of something like SQLite is, well, one is it's more complex than we need. It has a lot of features we're not going to use, and but also it's it's a C library, and so there's some binding things there that can be a little cumbersome, particularly for it's one thing to do this if you're a SaaS and running your service and responsible for the maintenance of it or whatever. But when you're like, here's a binary that you run, well, these kind of dependencies can be cumbersome. So we already have one of those with Envoy. It's like, do we really need to add more? So that was another reason, is that Pebble has a really good Go library. That's what it's written in. It was modeled on RocksDB. And so that was another reason went that direction. So that's kind of where we landed with the file-based approach. We did consider other things as well. So part of it is that we have a data broker interface in gRPC, a set of methods that we have to implement. And there are certainly other approaches to this problem, but they required significant changes to how we model data in the system. And if we had to do that, okay, we can pull that Band-Aid off. But as much as possible, let's just keep things the way they are, because otherwise we have to rewrite how everything works. And so where there are smaller changes that we could make that didn't require us to completely rethink everything, that still gave us what we were looking for. So that was part of it too. So, we could certainly have built a group cache approach, and maybe eventually we'll add that for certain types of data. But if that were everything, then how am I going to do the watching? How am I going to do there's this issue that we have that can be a real pain point with caching. I log in, and then I'm immediately redirected to another instance of Pomerium with my new session cookie. The session cookie, all it has is the session ID inside of it. It doesn't have the data associated with the session. And then I get to this other instance of Pomerium, and the session's not there. And so it's like, oh, you have an invalid session, and locks you out. And you get this infinite redirect login loop because you've outraced the data showing up at the other instance of Pomerium. So problems like that are things you have to worry about. Because Postgres solves that. It's the database. It's just another query on the database. But once you've gotten rid of that, then you have to start worrying about those kinds of things. So that was part of it too. Was trying to avoid some of the known issues that we've had.
Okay. Yeah, and like obviously making major changes, like you said, of how the data was handled, that just is potentially opening up a can of worms. Like the business value of all of a sudden getting all those bugs potential. Well, I know we write good code, but you know what I mean. But okay, so I was kind of curious. So like obviously we still support Postgres. We've got Pebble now for key value. Pebble is not a one-size-fit-all, though, right? You said it's for only if you're running with one node. Is that correct? Or did I?
Yeah, well, that's true. And so part of this too. So Postgres itself is not a highly available database. Now it can certainly be set up to minimize downtime with streaming replicas, failure detection and failover, and all those sorts of things. But I don't know if you've ever tried to do that. You kind of have to be an expert in Postgres to know how to set that up properly.
And here we are again.
Yeah.
So naively, most people have not set up Postgres in such a way. And that means if the database has a problem, you're just having downtime until you figure out how to fix it, frantically. Well, I guess these days you'd be asking ChatGPT how to get Postgres running again, and how to restore backup, how to, you just don't know how to do these things because you're not an expert. And so in reality, the high availability there is usually not been implemented. And even if it were, there's still several seconds of downtime. So if we want something that's more highly available or that can be distributed and replicated, how might we implement something like that was kind of the idea. If I have multiple instances of the data broker and if they all need to share the same state, how can I do that? So we kind of wanted to solve that problem too. And that's where we were looking at things like Raft. So if is that what we want to talk about?
Well, I mean, maybe just before we go there on Postgres, because I think it's just such a blanket recommendation. Again, I do want to unpack it, which is like, I think often when people are giving that recommendation, they are imagining like implied a cloud managed service that has a team of absolute killer Postgres experts behind it. And like, there's an abstraction layer to it. I don't know how often people are actually, when they're recommending, Postgres and chill or whatever, they really are talking about running bare metal Postgres, which is often where we're deployed, and does sort of need someone to have that level of understanding of the subtleties of high availability and recovery and all that stuff. They're kind of like hand waving away that it's been abstracted for them by Google Cloud or Amazon or whatever. So I obviously have a bone to pick here a little bit, because I think it just comes down to like there are like blanket recommendations for very good reasons in our field with data persistence. Postgres is a totally sane one, but like if I could do anything, it's like, if you fit this mold. And I think another one is SQLite, right? Another very sane choice. You probably have to exclude it away, but as Caleb brought up, it's like, we write our code in Go. And so, are you okay with C Go bindings and what that implies for a very complex Go code base? It is a big it could be a big change for how your code runs, especially at like the network layer. Like Go does some very subtle things just by using it, and so I think. Anyway, that's kind of my thing here. I would love to talk about Raft and what Caleb said. And so, yeah, I don't know how you want to kick that off. Distributed systems are like every programmer's favorite thing to think and then realize, man, do I not know this?
Well, I guess before you dive into that, Caleb, like we were saying, like, it's typically blanket suggested, and you're mentioning like all our clients are like self-hosted, and that's like actually a very big benefit of why people go with us. But again, there's that, like, to your point about the operator experience, so like we just have to make it not seamless, but like we have to make it pretty decent, but it's like, I just wanted to call out the self-hosting because like a lot of people, like I used to work at Netlify, so like it's at a pass, and like people are used to that kind of experience, a lot of people, but we're really focused on like self-hosting for a good reason. A lot of people have air gap solutions. There's security reasons why they do this. So like, just wanted to call that out before we kind of jump in. But yeah, sorry, go ahead, Caleb.
Yeah, well, on that point, a couple of things. So one is that managed Postgres has a lot of sharp edges at scale. And so they'll behave in ways that are unexpected. And you're just like, why is the database doing this? And it's like, I don't know, it's a magic black box. So there's a bit of that you run into. So it's like, you don't have to worry about all that stuff the cloud provider's doing. It's like, well, in the end of the day, you kind of do have to worry about some of that stuff. And then the second thing is, I worked at a large company. We use Postgres a lot. It's one thing if you're a SaaS company and Postgres is like your data store for everything, for all of your like core data. But you're willing to accept that, this thing going down is catastrophic and we have to get it running as quick as possible. And it's a core part of our business and all that. But when it's like, the edge proxy needs it, and we don't otherwise aren't using Postgres at all, that's like, it's not the same relationship you have with the database. And I will say, having looked at a large company that did Postgres, I was surprised. We had people who were very good with Postgres and knew what they were doing. But, 2 a.m, get paged, and an operations guy, he's like, oh, the main database has crashed. The node went down. It just died. And so it had to be replaced. And so he runs the script. We had a script, that he's following the playbook to do a failover. And the script fails. And it's like, master database not available. So it turns out we had written an entire playbook and backup script that only worked if the main database had not crashed. If this was the thing to recover the main database. So, I mean, this kind of stuff happens all the time. It's just like, you think you have this solved, and you don't when the rubber meets the road. So that's part of it too, is that it's a lot harder than you might think. But anyway, so as for the Raft thing, so yeah, actually a single instance of the data broker running the file store is probably pretty good. If the node dies, you could just bring up a new one, and everybody gets logged out, and you do have to redo the directory sync. But how often does that happen? How often does a node die? So it's not very common, and maybe you're just willing to live with an occasional outage from that. And I think for a lot of customers, that's probably sufficient. They don't need more reliability than that. But there are certainly some that would like more reliability than that. And in particular, not just the system is always available, but what's more important is, like, you can live with a few minutes of downtime if it fixes itself. That's like what people really want, is does not have to think about it. And so that's what got us in the direction of thinking about, can we implement some kind of clustering replication strategy that's self-healing? And so we were looking at things like Raft and other algorithms to do this. Go has it actually has 2 production-ready, reliable Raft implementations. One was in etcd, which etcd is the the sort of storage layer for Kubernetes. So like, it's hard to imagine something that's used more than that. Like that's pretty heavily used. And then HashiCorp has one as well that they use in their systems.
Is it underlying Nomad or quite a few?
Yeah,
actually?
Nomad and Vault, and then I know that CockroachDB also has, and I think probably other of these sort of more modern SQL databases that try to implement consistency on multiple instances. They use Raft as well, so it's used in lots of places. And we looked at actually implementing a truly consistent data store across nodes using Raft. We might still do something like that in the future. We might do it for a subset of the data. But the reality is we didn't really need those consistency guarantees, and they come at a cost. It means writes can be pretty expensive because they have to be replicated. And if we're already, if the kind of person who needs this solution is also the kind of person who's dealing with load problems, it's like, well, making the data broker slower isn't really going to help us that much.
Right. This goes into trade-offs, right? It's like if you need consistency, we still have Postgres, but if you don't, like here's option B for you, which is hopefully a much more performant, potentially self-healing thing. And the cost is like, I mean, to be clear, this is why like blanket recommendations are hard. Is like, what is the cost of this consistency for us? It's maybe a couple users who just logged in might have to log in.
Yeah. So instead, we're going with a model where we are using Raft, but only really to do leader election, and then we'll have a leader data broker and several follower data brokers. They are replicating data between them. If the leader dies, we can detect that via Raft and elect a new leader. And then that leader could take over with its state. And we're not guaranteeing that, user just logged in and, if that instance of the data broker crashes, that they will not get logged out. They might get logged out, but mostly the data is fairly up to date, and maybe we'll lose a few seconds. That's not really that much of a big deal. And that's kind of the trade-off we're willing to live with is an eventually consistent approach, but one that is self-healing. That's really what we want out of it, is that if an instance crashes, we can recover without anybody having to do anything at all. So
do we have any profiling on just how much faster, say that, like we're read heavy, right? Just like checking sessions, doing that authorization we do, like, I know this is still early, but do we have any like order of magnitude, how much faster it is for this set of trade-offs, or do you have a sense of that?
Well, I haven't actually implemented the fully fully consistent version. And so I'm not sure what the expense would be there. I was more just working off of what other people have said. And the fact that things like, if you look at CockroachDB, for example, the way they use Raft is very subtle, and they have lots of ways to get around the consistency guarantees in order to provide better performance. So those kind of flags were like, this is going to be a problem. It's also a lot more work to implement. So maybe it's not worth doing right now. In terms of performance, so this is the other tricky thing. If you run a local Postgres that is optimized, it can do a lot. You'll get very good performance out of it. Now, if you are running a managed Postgres where traffic goes over the internet, and you have a limited number of connections, and it turns out it's running on one core and has very little memory, well, that Postgres is really slow. So, and a lot of people, that's what they're running. And so, so the file-based version is maybe half as fast as the memory version, but it can do a lot. And compared to an improperly tuned Postgres is much faster. But it also depends on things like batching, and Postgres is much more susceptible to if you don't do proper batching, if your records are not the right size, if those kind of things, you can get very bad performance quickly. So whereas the on disk version is less susceptible to that, it kind of works either way. It doesn't really matter if they're giant records, a small number of giant records, or a large number of small records. It all kind of just works.
Yeah. Do you have a sense? I mean, that my follow-up question here is like, I know that sometimes, depending on the underlying data storage mechanism, like a bunch of small records is more efficient to store and read versus batching? Was there any change there? Does the underlying storage mechanism and how it handles batching versus not batching change how we handle data storage and retrieval, or no?
Yeah, so good question. Some of these changes we've already made to earlier versions of Pomerium, of lessons we've learned in that way. One lesson I learned is that my conception of data about users was not accurate. I thought that an organization would have a large number of users, let's say 10,000, and each of those users is probably a member of a few groups, less than 10. That is not true. As it turns out, most customers seem to have less users with a crazy high number of groups. And so that didn't quite work the way I thought it would. It meant that records were very large, much larger than I had anticipated. And that affected how many we batched as writes to Postgres. We were doing like several hundred at a time. And that was way too many because they're giant. I mean, the amount of data being sent over the wire was just very large. And so it's like actually all the benefit to batching was a much smaller number, like 64 or 32 or 16. You know, it's a good get down near there, and it's not going any faster with more writes, but the bad case of really giant records was less often. So we did apply some of those things. We also implemented sort of a smarter cache approach. So using those synchronization mechanisms we have in the data broker, we sort of pre-cache things. We just go ahead and populate it in memory cache with synced records because that data is already eventually consistent. And so we're willing to tolerate a delay there. And so we've implemented some of that as well. Just things like that, lessons learned.
Okay, cool. Yeah, and I guess one question I have, like you said, we've been talking about trade-offs and stuff, like with the file-based system, like with Pebble, like I guess just a general question. Sorry, yeah. And I know Bobby has to drop off shortly, but we can kind of wrap it up together, Caleb, if you're cool with that.
Sure.
Like, is there like a max? There's got to be like a max file size to like the Pebble file, right? Or like there's a trade-off there, I imagine, as well? Or
yeah, so definitely there are limitations there, though. Most instances of Pomerium should not have that much data stored.
Okay.
So, but Pebble, RocksDB, they're called log structured merge trees. The way they work is they store files that have sorted lists of strings in them and a write-ahead log. And periodically that write-ahead log is dumped into sorted files. And then those sorted files are all merged together to do lookups. Okay. It's very clever. It's based on LevelDB. It can, because of the nature of those files, they compress pretty well. And so generally there is some compression put on it, which helps to limit the file sizes. And it's not, it's actually a directory of files. So certainly that could be an issue, but I mean, it's kind of like, let's say you're running in Kubernetes and you want to host this file. The way you do it was a persistent volume. You can choose how big that persistent volume is. And in cloud providers, it's going to mount an EBS volume or whatever. So you kind of have, you have what you need to be able to get that right.
Okay, cool.
And these days, storage space is not usually that big of a deal.
Yeah, no, totally. Cool. I guess before we wrap up, anything else you wanted to cover, Caleb, or is that's pretty much that's kind of like the TLDR, pretty much what we've been working on lately with this?
Any parting advice, things you wish you knew before you did all this? Yeah,
like go up the curve, come down the curve, or not feelings.
So those consistency algorithms like Raft, those are pretty complicated. It's one of those things where to make sure it is actually working correctly is really hard. So you really have to think about it like this is not just something you can you can do in a few days. You really have to. It's going to take some time to get it to work. So, which isn't that surprising, but yeah.
Cool. Awesome. Well, I guess we'll wrap it up there. Thanks both of you for taking time today. I know we're all busy, so but this is great. For folks catching the recording later, we started doing these kind of deep dives with the team, so feel free to subscribe to all our channels and socials, and you can keep up with what we're up to. And we'll see you all in the next one.